Hello, my name is Jared Harrington, and today I'll be discussing my results from Lab 1 Constant Velocity. So in this video, I will go over the introduction, the physics principles applied in the experiment, the overall experiment, the computational code, the comparison and then analysis of the experiment model and computational code model, and then further questions that I'll have at the end of the video. So the purpose of this lab was to observe an object moving at a constant velocity, aka the same speed, without changing directions, and then compare the results to a computational model. Some key ideas that were found in this lab are Newton's second law, constant velocity, and net force. Also, Newton's first law is applicable in this lab. So to define Newton's second law, the definition is a force must be equal to the change in momentum over change in time. And if there is a constant mass, this can be equated to force equals mass times acceleration. And then I have the equation shown right here in the picture. So for net force and constant velocity, net force is the sum of all forces acting upon an object. And for this experiment, the task was to record an object moving at a constant velocity, which means there will be no forces acting upon the object. Thus, this makes the net force equal to zero, which Newton's first law says that if an object is at rest or in motion, that there will be no forces acting upon it, and we can clearly see that in this case it would apply. So for a preview of the experiment, so the setup was I rolled a tennis ball across a flat surface at a constant velocity. The system in this case would be the tennis ball, and then the surroundings would be the external forces acting upon the tennis ball, such as gravity, frictional force, applied force, etc. Some equations that were used in this experiment were the velocity update formula, which I have right here, and then the position update formula, which I have below. And then for the experiment itself, so what I did is I used the tracker app and I tried my best to get the center of the mass of the tennis ball in each frame, and then I tracked each frame like individually and then tried to get it within a straight line. And then as you can see here, I use a position versus time graph, and we can clearly see that this is a linear relationship in the positive direction. So for this, the mass would be negligible in this case, but I was able to calculate that. For the position, I saw the initial position using the tracker, and then for velocity, the initial velocity, I calculated it by getting the second position and subtracting it by the initial position, and then dividing it by the change in time, and then the change in time would be equal to 30 frames per second, and then when you divide that, it will give you 0.033 seconds. Here, the net force would be equal to 0, and then I changed or updated the velocity formula and then the position formula to match the equations in the earlier slides. So for the comparison of both models, at the first half of the graph, you can clearly see these two lines are aligned, but as time increases, these two models begin to separate, and this can be attributed to setting the net force equal to 0 in the computational model, but in the observed model, we cannot just assume that the net force is equal to 0 because we have to also account for frictional forces, gravitational forces, and other forces. And additionally, there may have been errors within the tracker system. I may have been inconsistent with placing the center of the mass of the tennis ball in each frame, and that may have caused problems within the graph. For the what if question, if I were to interchange the positive x position and the negative x position, that will cause the velocity to be a negative slope and cause the values for position to be negative. And then for the what does this mean question, it is difficult to determine or to get zero net force in a real life example, because you have to account for other forces such as frictional force and gravitational force, and you can't just negate that. So it is not possible to calculate how many pushes or pulls are observed. This is the end of my video. Thank you for watching.